Good evening to everyone. So myself PM Taplukatti. So lecture number 1 is Introduction of Stress and Strain for the subject Strength of the Material. The code is 18CP32. Okay, presented by myself, Professor PM Taplukatti. If I start the stress and strain, first we should understand the basics of laws of physics and some knowledge of mathematics. Okay, first the main whole engineering mechanics is divided into three categories. One is statics, dynamics and mechanics of the material. Static does not vary with the time, dynamics vary with the time, and the mechanics of deformable body, which means that you have to study the different behavior of the materials, and this subject is also known as strength of material, mechanics of deformable body, or mechanics of solid. These are all included in the same meaning. Strength of material, it is a SOM, MDB, mechanics of deformable body, and MOS, mechanics of solid, and one more is MOM, mechanics of material. These are all give the same meaning with respect to the different types of the branches. Those branches are mechanical, aeronautical, civil, and also IP, instrumental product engineering. Okay, first, according to the civil aspect, we should consider the strength of material. The strength of material is the study of internal effect and deformation that caused by applied load. Okay, which deals with the internal effect and deformation. Internal effect and deformation that will caused by the applied load. Okay, and the strength of materials depends on three main parameters. Those parameters are strength, stability, and stiffness. Okay, the strength, of course, the strength is nothing but the material which consists of some stresses. Those stresses value should be restricted to limited value. Beyond that limited value, we should not consider to the design aspect. Stability, the structure has to the structure has to stable with respect to the overturning, sliding, and frictions. And the stiffness, that should be the structure should be stiffness, which means that the structure is free from the some applied limits. Those applied limits are some deformation limits, some deflection limits, and some even flexural behavior, shear behavior. Those are all is nothing but it is a serviceability limit. Therefore, the strength of material is mainly depend upon these three parameters: strength, stability, and stiffness. Next is, we will start with the first topic, simple stress and strain. Introduction. The primary object of the SOM subject is to study the effect of external load on a deformable body. It is a effect of external load on a deformable body. The effect caused by internal forces and deformation. These internal forces and deformation are found by strength of material subject. The first term, stress. Every material is elastic in nature. Every material is elastic in nature. That's why whenever some external system of forces act on a body, it undergoes some deformation. That is true. Okay. When a rigid body is considered some applied load, there must be some deformations. The same point I explain here. Every material is elastic in nature. That's why whenever some external system of forces acts on a body, which will undergo some deformation. As the body undergo deformation, its molecules set up some resistance to deformation. Okay, its molecules set up some resistance deformation. These resistance per unit area to the deformation is known as stress. These resistance per unit area to the deformation is known as stress. Mathematically, the stress is defined as it is a force per unit area. It is a force per unit area. Okay. Therefore, the most common definition of a stress is the force per unit area is nothing but a stress. It is denoted as a sigma. The force is measured. The force is measured with respect to force P, and the area is measured A. Therefore, the P is a force, A is the area. The measurement of a force in either in terms of Newton or kilonewton, the measurement of a area either in it is mm square, centimeter square or meter square. Okay. So, please concentrate at the figure. Consider one body here, due to some applied load on the top and the bottom or a side. Consider these section plane cut into two pieces. These section plane cut into two pieces. Okay. This is a cut section. This is a cut section. Okay. When the load is applied on the one side, there must be internal resisting force normal to the plane it is. See here, this is a section plane now. Okay. This section plane has the same. Okay. The resisting force normal to the plane. Clear? Okay. And parallel to the plane is shear. Normal to the plane is, okay, which means that directly acting on the normal to the section plane is, okay, normal to the plane, and similarly parallel to the plane. Okay. See here, the P is a normal force and a Q is a shear force. Okay. Similarly, the P is a normal stress and a Q is a, P is a normal force. Similarly, with respect to stress is load by area. Okay, this load is acting on a unit area. Remember that unit area is very minute. Okay, unit area it is the force per unit area. Clear? Okay, therefore the force is either in normal to the section plane. With respect to shear force it is. Therefore, the P is normal force it is, and a sigma is normal stress. Okay, it is very simple concept. Consider the body, applied some load. Okay, when the member is cut into two pieces with the help of section plane, this section plane, see here, this section plane has a two funda. One is normal to the plane, the resisting force normal to the plane, and resisting force is parallel to the section plane. Normal to the plane is normal stress, parallel to the plane is shear stress. Okay. See here, consider the member subjected to load. It develops by resisting forces which develops a section in plane. Consider the each part which is in equilibrium under the action of applied load. The intensity of forces, the resisting forces split into two portions. One is normal and parallel to the section plane. Normal and parallel to the section plane. And therefore, see here, the resisting force parallel to the section is called shearing resistance. The resisting force normal to the plane is normal resistance. Keep it in mind. Okay. The intensity of resisting force normal to the sectional plane is intensity or normal stress. The intensity of resisting force parallel to the section plane is shearing stress. Okay. Therefore, see here, unit of stress is, one thing remember, it is very simple. Normal stress is the intensity of resisting force normal to the section plane is normal stress. Shear stress, the intensity of a resisting force parallel to the section plane is shear stress. Okay. Therefore, see here, if you consider for the unit of stress is always measured in terms of what? Newton per meter square, Newton per mm square. Okay. See here, if you consider for the units, very, very important topic it is, units. This is already known in your basic engineering mechanics. Unit of stress. In MKS, the stress is measured in terms of what? It is according to the basic definition. It is a load by area. The load is measured in terms of what? Kg force divided by meter square. In terms of centimeter square, it is kg force divided by centimeter square. Okay. See here, in SI, the force is measured Newton, kilonewton. Newton denoted as a capital N, kilonewton denoted as a KN. Clear? Okay, therefore, if you measure the area in terms of what it is, mm into mm square, centimeter into centimeter, centimeter square, into meter into meter square. Therefore, the sigma is equal to load by area. According to our basic definition for stress is what? Sigma is equal to load by area. Load is Newton, area is unit area, that is mm square. Newton per centimeter square, Newton per meter square. This is the unit of the stress. If we consider for the large quantity and a small quantity, okay, kilo, nothing but what it is a 10 raised to 3 denoted as a small k, mega denoted as a m 10 raised to 6, giga 10 raised to 9 capital G, tera 10 raised to 12, okay, capital T. If you consider for the small quantity, milli 10 raised to minus 3, micro 10 raised to minus 6, nano 10 raised to minus 9, pico 10 raised to minus 12. It is denoted as small m, mu, n and p. Clear? This is very, very important. Kilo, mega, giga, tera, milli, micro, nano, pico. If you take the length is measured always in terms of mm or a centimeter or a meter or kilometer. Okay? If you know the basic, 10 mm is a nothing but 1 centimeter, 10 mm nothing but 1 centimeter, 10 centimeter is equal to 100 mm. Okay? 10 centimeter is equal to what? 100 mm, 10 into 10, 100 mm. If you measure the, okay, this dimension into meter, 100 divided by 1000 is equal to how much? Because 1 meter equal to how much? 1 meter equal to 1000 mm. Clear? Therefore, it is 100 by 1000, 0.1 meter. Okay. If you consider for the reading is 25 centimeter, 250 mm, 25 into 10, 250 mm in terms of meter, 0.25. Similarly, 150 mm, if your length is 150 mm in terms of centimeter, 15 centimeter in terms of meter, 0.15 meter. Okay. And 1 meter is nothing but how much mm it is? 1000 mm and 100 centimeter. Remember, 1 meter is equal to 1000 mm, 100 centimeter. Okay, that is nothing but 10 raised to 3 mm, okay, 10 raised to square centimeter. If you consider for the area is measured in terms of what? Mm into mm square, cm into cm square, m into m meter square, kilometer into kilometer square. Okay, therefore 1 meter square is equal to, okay, 10 raised to 3 is 100 mm, 10 raised to 3 is 100 mm. Okay, that is 1 meter is equal to how much? 1000 mm square. Okay, 1000 mm square. That is 10 raised to 3 square, 10 raised to, okay, 6 mm square. In terms of centimeter, 10 raised to square into square, 10 raised to 4 centimeter square. Is it clear? It is very simple. The length is measured in mm, centimeter, and area is measured in terms of what? Mm square, centimeter square, meter square. And you should remember large quantity and small quantity. Okay. The next thing is, see here, stress is sigma is equal to load by area. Load is P, Newton per square meter or Newton per mm square. Okay, 1 Newton per square meter is equal to 1 Newton. 1 meter equal to how much? 1 meter is equal to how much? 100 centimeter. 1 meter is equal to 100 centimeter square. Therefore, 1 Newton 10 raised to 4 centimeter square. These 4 will get in the top portion, that is 10 raised to minus 4 Newton per centimeter square. Because 1 meter is equal to how much? 100 centimeter. Therefore, 10 raised to minus 4, 10 raised to minus 2, that is 10 raised to minus 6 Newton per mm square. Clear? Therefore, 1 Newton per square meter is equal to 10 raised to minus 6 Newton per mm square. Okay, is it clear? It's very simple. Here there is no confusion part. Okay, 1 Newton per meter square is equal to, according to the basic definition, 1 Newton 1 meter is equal to 100 centimeter. Okay, that is 10 raised to 4 centimeter square. This comes in the top portion 10 raised to minus 4 Newton per centimeter square. If I want the converted into mm now, okay, that is 10 raised to square, 10 raised to square, 10 raised to minus 4 minus 2, 10 raised to minus 6 Newton per mm square. Therefore, 1 Newton per square meter is equal to 10 raised to minus 6 Newton per square. Therefore, 1 Newton per mm square is equal to 10 raised to 6 Newton per square meter. This 10 raised to 6 is nothing but what it is a mega. 10 raised to 6 is nothing but what it is a mega. Therefore, it is 1 mega Newton per square meter. Okay, 1 mega is equal to how much? 10 raised to 6. Similarly, 1 Newton per square meter is nothing but 1 Pascal. Okay, it's very, very important. 1 mega Newton per square meter is equal to 1 Pascal. Okay, that is Pascal denoted as a PA. Pascal denoted as a PA. If you consider for the conversion, okay, see here, conversions are very, very important. Okay, 1 kPa, that is kilopascal. 1 kPa kilopascal, 10 raised to 3 Pascal, because 1 K is equal to how much? 10 raised to 3, 10 raised to 3, okay, Newton per square meter. That is 10 raised to 3 Newton. 1 meter equal to how much here? Mm? 1000 mm square. 1000 mm square. That is 10 raised to 3 into 2, 6. 10 raised to 6. 3 minus 6. 3 minus 6 will minus 3. Therefore, 1 kPa is equal to how much? 10 raised to minus 3 Newton per mm square. Remember, 1 kPa is equal to 10 raised to minus 3 Newton per mm square. Therefore, your readings, your trial readings of a stress is 50 kPa, 50 into 10 raised to minus 3 Newton per mm square, 70 minus 10 raised to minus 3 Newton per mm square. If it is 100 kPa, 100 into 10 raised to minus 3 Newton per mm square. If your reading is 250 kPa, okay, that is 250 into 10 raised to minus 3 Newton per mm square. If the same reading is 1 MPa, M stands for mega, 10 raised to 6 Pascal, 10 raised to 6 Newton per mm square. Here also same, 1 meter equal to 1000, 10 raised to 3, 6. That is 10 raised to 6 minus 6, 0. But the quantity will become 1 Newton per mm square. Therefore, 1 megapascal is equal to how much? 1 Newton per mm square. 1 mega Newton mm square. Okay. Similarly, see here. Okay. That is, if your reading is 40 MPa, 40, simple, 40 Newton per MPa square. If your reading is 200 MPa, 200 Newton per mm square. If your reading is 120 MPa, 120 Newton per mm square. 20 MPa, 20 Newton per mm square. Okay. Similarly, if your reading is gigapascal, 10 raised to 9 Pascal. Okay. Giga means what? 10 raised to 9. 10 raised to 9. 10 raised to 9 Newton per mm square. Okay. 1 meter equal to 1000. 10 raised to 3. That is 10 raised to 9 minus 6. Remaining quantity will be 10 raised to 3 Newton per mm square. Therefore, 1 gigapascal is equal to how much? 10 raised to 3 Newton per mm square. If your trial reading is 60 gigapascal, okay, in terms of Newton per mm is equal to how much? 60 into 10 raised to 3 Newton per mm square. If your trial reading is 85 into 10 raised to 3 Newton per. If your trial reading is 120 10 raised to 3 Newton per mm. This is also denoted, also rewritten as 1.2 into 10 raised to 5. Here you will not confuse the part. Okay, it is very simple. 1.2 10 raised to 5 Newton per mm square. If your reading is 160, okay, GPa. Sorry, it is GPa. It's not an MPa. It is GPa. Okay. 160 into 10 raised to 3 Newton per mm square, 1.6, okay, 10 raised to 5 Newton mm square. Okay, we'll stop with the today's session. We'll continue with the, okay, next class. Okay, thank you.